And this is from the bird view perspective. You can see we encounter a view of discontinuity, which divided into two different orientations. The red line is the first set of discontinuity, and they have orientations at not 25 degrees, while the yellow lines are the second set of discontinuity, and they are relatively on not 260 degrees of orientations. And as you can see, it is widely intercepts. Next. The green zone is the landslide block. So all of the landslide material that we see before is coming from this failures block. And finally, within this couple of data, we can jump to a new conclusions that the failure mechanism of the landslide is a wedge failure, not a circular failure. Next. So how come this happens? Well, the landslide is occur near the geological fault axis. The fault of the geological faults is formed by compressive force. And as what FGBL said in his book, that there are generally three different joint sets that might occur in the axis of this fault. It was diagonal joints, who has the minimum stress, longitudinal joint, which has the intermediate stress, and cross joint, which has the maximum stress. And sometimes, due to its lateral constraints of subsurface, the joint might not manifest themselves in a physical joint yet, but the stress exists. The stress exists, and at least at two different directions of stress. And then if we open the lateral constraints by excavations, followed by mining activities, and also blasting activities, stress relaxations happens. And when stress relaxation happens, the stress finally have a chance to manifest themselves in a physical form as a discontinuity. So in the initial investigation, it might we might not find any kind of discontinuity data, but then after we excavate it, we blast the slope, we excavate the slope. Uh, the joint might occur because the stress finally have this kind of stress relaxations. Next. The interesting point is that in this case, they don't really realize what kind of failure mechanism they need to deal with. So they do analyze the factor of safety on their designs at the very beginnings, but the analysis that have been done is using 2D limit equilibrium, as you can see in the presentations, and recognize it as a circular type of failure. While in reality, they're dealing with wedge failure, which not enough if we only use 2D analysis. The result of the 2D analysis provide a safety factor of 1.7, so it is safe, and the probability of landslide is only 0%. But the 2D analysis limit equilibrium has a limit, not being able to analyze the presence of wedge failure or wedge planes in 3D. And this 2D analysis is only focused on the shear strength of materials, such as cohesion and V, not the discontinuity. And the probability of failure analysis is obtained is only from analysis of variation on the shear strength. The analysis was carried out using a circular failure, depending on the failure of shear strength. And the analysis that you see is not considering any kind of presence of discontinuity planes on the mine slope. Next. Well, we need to understand at the very beginning what kind of failure mechanism that we're gonna deal with our mining site. And we need to understand, is this type of failure mechanism can be analyzed only using 2D? Is it really enough using 2D analysis? Or you might deal with 3D problems, like these wedge failure mechanisms. You might use 2D analysis on plane slip surface analysis, or rockfall analysis, or even toppling. But wedge failure is a 3D problems, and you cannot account this type of failure using 2D analysis. Yes, you might analyze it using kinematic analysis, but still this kinematic is have their own limitations, such as the location of wedge failure is cannot be defined using using kinematics. So as for my conclusions is that the only software that suits best for this type of problems is using 3D analysis from slide 3. Slide 3 is the best options to analyze the factor of safety of wedge failure, and using Breum, the discrete plane can be defined easily. The positions of discontinuity, also the depth and the directions or the orientations of the discontinuity can easily define in slide 3. And Edison will show you how to do it. Edison, please.
Thanks, Gilang. These next slides present a similar case study as to what Gilang presented, in which the pit configuration includes a bore nose. In this example, if we simulate similar pit conditions where persistent joint planes transcend the bore nose, we can readily model the failure mechanism in slide 3. In this model, I've applied an anisotropic material model to simulate weaker ubiquitous joints that have the potential to form a wedge or planar failure through the bore nose. The results are a factor of safety of less than 1 that simulate a sliding failure mechanism through the bore nose. These next few slides show different perspectives of pre-failure geometry on the left and the geometry of the critical failure surface on the right. And from another perspective, we can also display different features of the critical slip surface, such as the dip of the column base, to interpret the failure mechanism. In this case, validating a portion of the critical slip surface is sliding along the weak subvertical joints defined in the anisotropic model. Building a slide 3 model. There are 4 ways to build a 3D model within slide 3. You can import and extrude a slide 2 model. You can import surfaces and volumes that were generated in other 3D CAD, geological, or mine planning software. You can use the CAD drawing tools within the software, and you can import a block model created in external geological modeling software. This is the function that I'll demonstrate in this webinar. When setting up a block model, you can either predefine your material properties or import the material property names from the block model and then assign material properties. In this example, I'm going to import the block model first and then define material properties. So moving to a live session of slide 3, I've opened up a new project. Within the software, we want to select materials and then define materials. First, I'm going to add a new material and rename it block model. I'm then going to select block model from the failure criterion drop-down menu and select new function. I'm going to rename this new function, for example, August 2021, if it's a current export from your geological modeling software, and then import block data. Before we import the file, I just want to show you what it looks like. So the file we're going to import will include the X, Y, and Z of the center of each block and the material name. You also require other information such as block rotation, block size, number of blocks, and the starting corner of blocks. This information can be saved in the import file or recorded when you export the data from the original block model source. Okay, back in slide 3, I'm going to select the CSV file to import. And now I need to define which rows and columns the data I want to import begin at. So the starting row in this example will be row 8. The software is now generating external volumes for each of the imported blocks. For those that are familiar with slide 3, you can see from the padlock icon that we now have our external boundary defined based on the geometry of our imported model. And now our 4 material types are defined using the block model import file. We can now go and add additional features to the model, such as new materials or weak planes to compute a factor of safety. This example is in the tutorials and has just under 3 million blocks at block spacing of 3.7 by 3 by 2.1 meters. Now to show a couple more examples of imported block models. This one with a weak layer added after the block model was imported and created. The results on the left show the factor of safety as imported, and the results on the right show the factor of safety after a weak layer has been added to the imported block model. You can see the critical slip surface is now sliding along the weak layer that was added to the block model. This is another example to show you a block model which had 28 material properties imported, covering a distance of 3 by 2 kilometers in dimension, and with the results contoured as a surface safety map. In this example, a total of nearly 13.4 million blocks were imported at 10 by 10 by 5 meter spacing. Moving on to search methods, these are the different methods available in slide 3. You can search by grid, auto-refine, cuckoo, and particle swarm, and then also apply search filters by elevation, volume, depth, and weight. I'm now going to show you results of a case study. Different search settings have been applied. This is a simple open pit mine with 4 materials, all isotropic. At default settings, the factor of safety reporting at GLE is 1.85. If I select show all surfaces, I can now see where the slip surfaces were generated. A question for online attendees: is there adequate search coverage? No, not really. You can see very few slip surfaces have been generated in at least these 3 locations highlighted by the grey polygons. So do we know, or are we confident that we've actually found the critical slip surface? In the next iteration of the same model, I increased the number of nests from 20 to 40, which increased the number of slip surfaces generated from 830 to 1658, and marginally reduced the factor of safety from 1.85 to 1.8. What is different here, though, is the location of the critical factor of safety. Previously on the southwest facing section of slope, and now at these greater search settings, the critical is located in the southeast section of the slope, previously with very low search coverage. The next iteration I ran was with all analysis methods selected. Previously, I was just searching for the critical GLE, and now I'm searching for the critical using Bishop, Yambu, Spencer, and GLE analysis methods. At these search settings, the critical factor of safety is located in the same region of the slope as the previous iteration, and the critical factor of safety has reduced marginally from 1.8 to 1.77. The reduction in factor of safety in this iteration is attributed to the search settings, where the optimization function is based on all results of all critical factors of safety calculated for each analysis method. So it's recommended that you always compute with all 4 analysis methods selected and then report with your preferred method. A powerful way to search for multiple minimas in 3D models is to use the particle swarm multimodal optimization search function. Here you can define how many low factor of safety slip surfaces to optimize based on their distance apart from each other. Searching for the 4 lowest critical slip surfaces, the particle swarm MMO search function has located 3 in the southwest facing section of slope and the 4th in the north facing section of slope. But looking at the results when show all surfaces is selected, have we adequately searched the whole area at these search settings? Again, probably not. So the next step could be to either increase the number of particles in our search or to find search limits to concentrate searching in areas of low coverage. In this next example, I've added a search limit to the western section of the slope and selected completely inside, so all slip surfaces generated must be within the defined search area. Contouring the results, we can see the sections of slope with the lowest factor of safety are in areas we previously identified using both cuckoo and particle swarm search methods. Selecting appropriate search settings. So what to use? In this example, the critical factor of safety across all iterations was greater than 1.5. So assuming our design acceptance criteria is a minimum factor of safety of 1.2, would it have really made a difference what search method we applied and whether we completed sensitivity analysis with different search settings? What if our initial cuckoo search results look like this and the critical factor of safety was 1.2? What other tools do we have available to assist us in the selection of search settings to find the critical factor of safety in our slopes? Within the Rock Science suite of software, we can import Slide 3 models directly into RS3, same as the process of importing Slide 2 models into RS2. We can then run a fast elastic analysis to help guide on where low factor of safety areas might be located, so we can refine search settings and search locations in limit equilibrium models. This is what I've done with this second case study, imported the Slide 3 model into RS3 and run an elastic analysis. Looking at the results, and this model literally took 5 minutes to generate and compute, we can now use the highest computed displacement areas as relative indicators of slope stability. I can now use this information to focus my search in Slide 3. For example, if I recomputed my second case study using a particle swarm MMO search method and applied a search limit to the western section of the pit that showed the most displacement in my elastic analysis, these are the updated results. I'm now presented with 3 low factor of safety areas, all equal to or less than design acceptance criteria. So that brings us to the conclusion of this open pit stability analysis using Slide 3 webinar. Some key points to leave you with. Preconceive the failure mechanism or mechanisms to determine the most appropriate tool or tools for stability analysis. Complete sensitivity analysis with different search settings. Look for multiple low factor of safety areas in 3D models. Use another method to reconcile or validate results. Finite element analysis is a powerful search method in that no assumption of slip surface or critical surface location is required prior to computing. The new block model function is a fast way to build 3D models in Slide 3. And if you'd like to trial any of these features, sign up for a free trial at Rock Science's website. Thank you for joining this webinar. If you have any questions, please feel free to input them into the chat box. Any questions from the audience?
Baik, terima kasih ya Bapak Ibu dosen sekalian. Tadi setelah kita mendengar sejarah dari topik, tentu sudah dilengkapi ya. Saya pikir saya coba share screen sebentar.
One of the questions is, how long did it take you to set up and run these stability analysis, especially for the colored map you showed in the beginning? This was a relatively simple pit geometry, so I used surfaces that were readily available from the geological and mine planning software. The model probably took about 15 minutes to construct. Each iteration maybe took 5 minutes to calculate. And then the contoured safety map is just a way of summarizing the results that are calculated. And that's generated within less than a minute based on the results. Getting some other questions. So for that question was from the block model. The block model probably took about, the one with nearly 28 materials and 13 million elements. That one took about 15 minutes to import and construct, and then the calculation was within about 10 minutes as well. That depends on the compute power as well that you're using. Another question from slide 3, is it possible to manually draw the separation of materials in the stratigraphy without the need to export from Civil CAD or the borehole manager module? Yes, absolutely. There's CAD functions within slide 3 where you can manually define boundaries or planes or loft planes to create your own boundaries or lithological boundaries within the software. I've constructed a few 3D models and all of them has ended up with a higher factor of safety result than 2D, even though the geometry was unfavorable and anisotropic properties applied. My question is, how confident can one be in the results of slide 3 and RS3? I'd have to say this is going to be model and material specific. If you have those models and you'd like some feedback, please feel free to contact us at support@rockscience.com or email the models directly through to us, and we can assist you to reconcile the results between 2D and 3D. Which is the correct way to introduce containment elements in the stability model, such as retaining walls, piles, and anchors? Probably if you're looking for deformations of those structures and capacity, this might be more of a finite element problem than a limit equilibrium problem. Again, if you've got a specific problem or case study that you have questions on which would be the best tool to use, please feel free to email us and we can guide you on what we have within the RockScience suite of software, which would be the most appropriate. Does slide 3 handle very complex 3D geological models? Yes, we've certainly had very large or success with open pit models for deep diamond mines, deep gold mines. There's several papers that have been published showing those examples. We'll be sure to send a reference list with this webinar, but yeah, I can say that complex hard rock mines up to 400 meters deep have been successfully modeled in slide 3 to back analyze failure mechanisms observed in the pit. And those failure mechanisms and critical slip surfaces have been validated using the overlay of monitoring data that you can readily import into slide 3 and RS3 software. How does it compare to Plaxis and other geosoftware? Slide 3 is limit equilibrium. Plaxis traditionally is numerical. Again, we can list some references at the publication of this webinar that shows some comparisons, some specific comparisons of rock science software with Plaxis. Generally, there's very good compatibility of materials and results between the two. If we only have Dxf files, how can we import the Dxf file and set up the material model using only slide 3? If you've got the Dxf files from your geological modeling software or your mine planning software, you can import these directly using import geometry. There is a webinar, if I can skip back. We do have a webinar on Rock Science's YouTube channel, see the open pit mines modeling and analysing webinar, which shows how to import deficits and construct a 3D model. The same process would be applicable for RS3 as well. Can pore pressure be exported from slide 3 to RS3? Currently, slide 3, you can import HU and RU coefficients. Those can be exported to RS3 with material properties. Slide 3, unlike slide 2, doesn't currently have a finite element groundwater package. But if you have access to RS3, RS3 has the groundwater, the finite element groundwater modeling package in there that you can then export results, including an isosurface, back into slide 3, which can delineate the water table. When you talk about sensitivity analysis, what were the selected parameters? In this webinar, it was mainly the search settings. So the different examples that I went through were using cuckoo and particle swarm only, and then looking at the number of nests or iterations that you can select within cuckoo and particle swarm. It's really important whether you're modeling in slide 2 or slide 3. Would really recommend using the show all surfaces option after you or when you're interpreting results to ensure whether you're modeling in 2D or 3D that you've adequately searched the whole section of slope that you're looking for. And show all surfaces is a nice tool that gives you a graphical display of where slip surfaces have been calculated in your model. So we should predict the weaker zone block before and then try to simulate in different perspective. What properties data do we need to input, whether in hard rocks or weak rocks? Whatever modeling software you're using, I think it's important to have an understanding of the failure mechanism before you start modeling, so that way you can then select the most appropriate analysis tool. So yes, that would include an understanding of where a weak zone or weak planes are located. And if it is back analysing a failure, if you do have survey data from the field, what properties data do we need? So for slide 3, it's exactly the same as slide 2. What material properties for your rock mass, weak planes. If groundwater is affecting your stability analysis, you need to have that as an input as well. The block files are lighter than Common CAD geometry files. I guess it really depends on the size. They can be, from my experience, that generating that model with 13 million blocks to do that in a matter of 15, 20 minutes. Would have been a lot faster using the block model import as opposed to importing each of those material boundaries one by one and dividing all into a model. But I guess it gives you the flexibility now in the software that if you do have access to a block model, you can complete that as a sensitivity analysis. And you've also got the option, if you only have surfaces or volumes, to create a 3D model using the traditional approach as well. I'm new to this software. May I ask if I get the block model .csv at the first place? This would be exported typically from your geological modeling software. So from log, there would be export the block model based. And I said, as long as it has that minimum information, the X, Y, and Z of the center of the block size and material type, that should be enough to get you started. Again, if you do have geological modeling software and are not sure how to export in the required format to create a block model, please contact us and we can assist you to export that and then import it into Slide 3 software. How to construct the groundwater surface in 3D to support stability analysis. Good question. We do have another webinar on Rock Science's YouTube channel. It shows how to generate a groundwater table using RS3 and then import that as a surface back into Slide 3. Otherwise, I've seen customers, if they don't have a groundwater surface, they may use the slope surface as a starting point, drop the slope surface in elevation, and then change the HU parameters for each material property. What is the basic of data which we input in Slide 3 from MindPlan software? Is it a block model or topography? So you can use either. That's the nice feature about block model, this new function. If you do have the geological model, it's very fast now to create a 3D model using that as a template. Otherwise, yes, survey data, a DTM to create your external surface. And then from your geological software, if you've got surfaces or volumes, you can export and import those into Slide 3. Also, if you've used borehole editor, if you don't have these surfaces predefined, but you have borehole data and you know the X, Y, and Z of each borehole, you can input that into the software and then create surfaces from your borehole within Slide 3 and RS3 as well. Same as what you can do in Slide 2 and RS2 with borehole editor. What block model generation software format work best with Slide 3? Slide 3 is designed to be as open as possible. So I guess the ones that we've typically used to date are Leapfrog, and I think Deswik and Serpac. But again, if you have a specific geological modeling software that you can generate a block model from, feel free to contact us and we can assist you to import it into Slide 3. Can we input surface lithology data from Mindscape Strat model to define lithology in Slide 3? Yes, any surfaces, as long as they either fully intersect the external boundary or another volume within the software, they can be used to create new volumes in Slide 3. What rock science software that you recommend for civil construction work, such as slope stability, foundation stability, soil improvement? I guess it completely depends on the solution or the problem you're trying to solve, but typically civil works would would use anything from Settle3, RS Pile, Slide 2, RS2, and then through to Slide 3 and RS3. All of those programs are available to trial for free on our website. Just connect and then request a trial, and we'd be happy to set you up with 10 licenses if you have a specific problem that you want to trial with new software. How to define stress relaxation factor in rock science software. I'm not sure if you're referring to SRF, but anything to do with, I guess, deformation, you would be looking at finite element, so RS2 or RS3. Have you used the results of a slide 3 to integrate them with a BIM model? If someone could elaborate what BIM, what the acronym there is, please, I'll try and answer that question. Does slide 3 handle imported UAV survey data well? They can be quite large and detailed. Do you need to simplify the Topo UAV data before importing? It depends. So if you have a high resolution file that you need to retain that resolution for the specific problem that you're modeling, I wouldn't recommend simplifying. But if you can have the capacity to reduce some of the resolution in those files, I would do that in the survey software. So from experience, MapTech, they've got a simplification tool. Rock Science software also has a simplification tool when you import. But I guess if you can bring a smaller file into the program initially, it's going to be faster to import again. So it all depends on the level of detail that you are required to retain. Rock Science does have minimum specifications for software. So I guess at the bare minimum, if you are using these larger data files, we would recommend going for the recommended computer specs or above, not the minimum if you are looking to process quite detailed topo files. But yeah, certainly most of the slide 3 models, RS3 models I've built have used real survey data to define the external. For a wedge failure consisting of more than one weak plane, is it practical to include multiple planes of weak surfaces? So there's multiple ways that you can model wedge failures within slide 3. Obviously, Rock Science has S-wedge as well, that you can model up to 5 release planes. Within slide 3, as I showed in the example, you can either do it by defining weak structures as ubiquitous joints, or you can define it as a combination of ubiquitous joints in an anisotropic material model with user-defined weak layers. And they also have a specific wedge search function here. So you can see here the different search methods. One of these up here is wedge, where you can specifically define 2 intersecting planes and a point of intersection. So it'll calculate the factor of safety of that specific wedge you've defined, or you can define 2 intersecting planes, and the software will, I guess, float those planes through your slope and find the location where those planes intersect that has the lowest factor of safety as well, for user-defined dip and dip directions of release planes. Can we construct the groundwater surface model by time so we get and see an understanding of the changing factor of safety of stability by time? You can, if you've got the groundwater surface and I guess potentially different elevations, topo elevations, that would just be separate slide 3 files. Otherwise, you could certainly model that in stages in RS3. What are the main advantages compared to Slope W or GeoStudio? Good question. I think, from my perspective, it's the integration of the software between each of Rock Science's products. Rock Science are certainly market leaders and do a lot of research into finding new algorithms to try and find the critical factor of safety. In slide 3, we work with industry partners such as IDS, GeoRadar, GroundProbe, Roytech, 3GSM. So we're trying to work with as many industry partners as well. So our customers, other service providers or software providers or hardware providers that we share common customers with. So I think that's an advantage of Rock Science. We're always trying to improve the product across the range of application it might be applied in, just not a stability analysis. And as I said, the integration of software within our product suite. So the integration of DIPS into Rockplane, S-Wedge, Rock Topo, and then the integration of slide 2 to RS2. Then we can go slide 2 to slide 3 to RS3. So I think they're some of the strengths of Rock Science software and the technical team that developed the software in Toronto. My question is on RS software. Take RS2, simulate a rock, put an applied force in it, and then in the dynamic model, simulate, see the stress wave is propagating. I think send us an email on that specific question. We can certainly do dynamic loading, and you can apply different forces, be there an external force or a support force. So if you have that specific problem, please send us an email and we can guide you on what functions within the software you analyze that. That's great. Thank you everyone for your participation today. As I said, we'll have some references to add to this webinar when we put it up, based on publications of where slide 3 has been applied in large open pit mines. And yep, please feel free to try the software and have a great evening or afternoon wherever you are for joining. Thank you.